At a conference in February of 2020, Andrej Karpathy discussed in some detail the problems and solutions Tesla has experienced creating their amazing autopilot software. Let's take a look and find out what he and the team have done. Hey y'all, it's Dr. Know-It-All. This is part 2 of a series I'm doing helping to explain what Andrej Karpathy, Senior Director of Artificial Intelligence at Tesla, and his team are doing. Check out part 1 above if you're interested. Also, by the time I got done looking at Karpathy's presentation, which is about a half hour long, I realized that we need to split this episode itself into 2 parts. So part 2 of this particular talk will be coming soon. Let's discuss part 1 now. The talk I want to break down is from the Matroid conference on February 26th and 27th of 2020 at the Computer History Museum in Mountain View, California. Yes, this was during that fabled time before we were all stuck at home with our masks on. Wow, what an amazing life it was. So the conference itself was all about computer vision, and it was practically in Andrej's backyard, so it makes a whole lot of sense that he would give the talk here. The talk itself is linked in the description if you want to check it out. I highly recommend that if you want to see the original source. Here I will hit what I think are the most important highlights for you and explain parts that might be a little bit technical for the layperson to understand. So here goes. First, after some introductory problem statements, Karpathy outlines Tesla's general approach to solving full self-driving. And this is what he calls it during the talk, so don't get on my case about that term. I know it's like everyone's like, full self-driving, enhanced navigate on autopilot, etc., etc., etc. He calls it full self-driving in the actual talk itself, so that's what I'm going to go with. Also, a little side note that I had not realized before, the new cars that Tesla's coming out with spells cars. In other words, Cybertruck, ATV, which yes, of course, they haven't really announced that, but it's sort of their Roadster and Semi. So yes, the entire lineup of current plus future cars spells sexy cars. And I was just like, oh gosh. Geeks on parade, man. So at this point in February of 2020, Tesla had about 1 million cars on the road. Now that's probably closer to 1.5 million, but anyway, that's what he had to deal with at the time. So all of these cars are data collecting and data testing machines, as we've discussed here a number of times before. And as noted in this video, Karpathy calls them robots as well.
And they're also robots. So they have sensing, they have actuation, and we're developing the brains of that computer.
I have a video about that here. For basic autopilot, which is the included software with every car, he had about 3 billion miles collected up to them. For enhanced navigate on autopilot, they had about 1 billion miles driven at the time. They had 200,000 automated lane changes and cars driving with this feature in more than 50 countries, which is actually really important when you think about global distribution. And the fact that they have 50 different versions of the software is like, oh. Again, I just can't believe how complicated this whole project is. Karpathy starts out by discussing a number of always-on safety features to keep the car safe, including one that might be unique to Tesla, an emergency acceleration which can allow the car to accelerate rapidly to avoid rear-end collision, which is super, super cool. It's important to note here that all of these safety systems are running in the background automatically, whether or not you're running any kind of autopilot software. Karpathy shows a couple of real-world examples where the cars avoid hitting pedestrians, which is super cool.
Really, what are we talking about here? Pedestrian A/B is the following. Here's one example. The car just, someone just emerges from in between parked cars, and this car may not have even been on the autopilot, but we continuously monitor the environment around us. We saw that there's a person in front, and we slam on the brakes automatically. Here's another example. It looks like a pretty benign scene. This person is probably not paying attention. The pedestrian is not paying attention. We slam on the brakes and prevent a collision. Here's one more example. You can see the trouble coming from the right. It's really hard to tell because everything is occluded, and then suddenly there's a pedestrian. We slam on the brakes and avoid a collision again.
Then Karpathy turns to full self-driving. At this point, this was only for developers, so you can see that the interface is very, very rough, but it looks an awful lot like the beta version, which is now out for a select group of people. And so the functionality, while it's not quite the same in the one he's showing, the visuals are much more similar to the beta version that people are using nowadays. So the first thing Karpathy does is compare a Tesla left turn to a Waymo left turn. As he notes, Waymo's been making left-handed turns, which is the most difficult in right-handed driving countries, of course. And you think like, no big deal, why is Tesla taking so long? But he talks about how it's different with what Tesla is doing versus what Waymo has done.
A Waymo comes to an intersection, and takes a left through the intersection. You've seen this for a decade. So how is this special? Why are we so late? What's taking so long? And it looks the same.
So first, of course, he discusses how vision versus LiDAR is a really, really big deal. So obviously, Tesla uses vision and not LiDAR. And second, and more importantly, really, Tesla does not pre-map the areas. They use general maps like Google Maps or Apple Maps or something that give a sense of the area, but not the precise maps that Waymo and other companies like GM Cruise are depending on in order to drive in those areas.
And we do not build high-definition maps. So when we come to an intersection, we encounter it basically for the first time. We come to an intersection, how many lanes are there? Left, right, center? Which way should I turn? What are the traffic lights? Which lanes do they control? All of this is just done just from camera vision alone. And so this is a bit of a harder problem, but of course, once we actually get this to work, we can also deploy it to the millions of cars that we have globally.
What this means, as Karpathy says, is that the car has to create the map of its location like a human being. It has to see it, and it has to project its sense of space from its eyes or sensors. Karpathy then gets to the fun stuff, how the neural networks that make this all happen work. So first of all, road layout. What do the lane markings tell us about how many lanes there are, where the ego car should be, etc., etc. Then it's got to identify all of these objects which are on the road. It's then got to know which are going to stay still, which are static objects like traffic cones or street signs or trees, and which ones are going to move or be dynamic like cars and pedestrians and a garbage bag blowing across the street, etc., etc. Karpathy then turns to one of my favorite terms, which is semantics, and that is what is the meaning behind each of these scene elements. Like, what does a traffic cone mean? What does the right turn arrow mean that's painted on the road? What is a car, etc., and what can it do? In other words, once you have your objects, you have to create meaning from the scene. And I have a video about that up here, so you should definitely check that out if you're interested in more information about that.
So we have to understand a lot about what are the static objects, what are the dynamic objects, what is the road layout, what is all of the layer of semantics on top of the road, like lane line markings, road markings, traffic lights that tell you about how you can actually traverse that scene. So once you actually start writing down what's necessary to actually perform the driving policy, you end up with a long list of tasks, all of which we need to actually handle.
Also, while Karpathy doesn't really bring this up, note that this is going to change in every single country as semantics like the language, the units of measurement, the meaning of painted signs, etc., 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 change. So this is an absolutely huge job. Note that they're able to keep the frames per second up to like 17 or so frames per second, and that's incredibly difficult. As you can see from the clip, lanes are being detected, as is the truck ahead of the ego car. It also notes that there's a wet road. I don't know how it does it. Maybe it's because it's shiny, but that's super cool too, as well as signs and other important elements in the scene. For example, the stop sign, which means it needs to stop. And all the while, it's maintaining 17 frames per second, which is absolutely nuts that it's able to do all that work that quickly. Also, the boxes in this sample scene are really, really useful to see. This indicates that the vision detection system is segmenting out the visual and extracting the important elements of the scene for analysis and doing it in 3D because it's making boxes, not just squares. So it's projecting a three-dimensional world out of two-dimensional vision. Also note that the buildings and trees and other unimportant elements are being ignored, and that's just as important as identifying what's important. It's important to identify what's not important. It's a very complicated way of saying it, but that's the right thing. All of this is just a huge achievement, and it's still mind-blowing to me that they're able to do this. Also, as Karpathy talks about, there's apparently an attribute list for everything. For example, parking lines versus street lines, etc., etc. And that's really cool. That means that they've created kind of a dictionary or something that gives meaning to all of these semantic objects. So the vision system basically says, what is this? And once it identifies it, it's able to then use a dictionary or something like that to say, like, what is this thing and what are its attributes? In other words, a parking line or something, don't really worry about that. But if it's the side of the road, if it's the street line, then you have to obey that and stay inside of that. So it's really cool that they have this attribute list. I'm sure it's a very big one that's allowing the car to make determinations about what to do once it identifies each individual scene element. In a moment, let's talk about stop signs. But first, if you enjoy this video, definitely like and subscribe so you can see the second part of this particular video. Also, we have a 10,000 subscriber giveaway going on until January 5th. Check out the link in the description for more on that. Also, as always, a big shout out to my patrons on Patreon. You all are wonderful. We have a new patron since the last video, Thomas Keck. Good to meet you. Thanks so much. Also, a big thank you to Zenly Music for doing the intro and conclusion music. He's an amazing artist, so definitely check him out on YouTube or Instagram. And finally, if you're interested in a Tesla yourself, click on our referral link in the description. And if you use that, we both get 1,000 free supercharger miles, which is cool.
Even taking a very simple task, like for example, stop sign, you think that neural networks are capable of handling thousands of categories of ImageNet with all of their variations and so on. So how difficult is it to just detect a fixed pattern of like red on white stop? And it actually gets quite difficult when you get to the long tail of it, even to create a simple detector for a stop sign. So first of all, stop signs can, of course, be in lots of variant environmental conditions. Stop signs can not just be on poles, but kind of just like on walls. Stop signs can be temporary and just hang out in different configurations. Stop signs can have funny lights on them, which are supposed to make it easier to see the stop sign, but for our system it's the opposite. We have to actually explicitly worry about it. Stop signs can be held by a person. That stop sign can be in an inactive state or an active state. Stop signs can be on like these cones. Stop signs can be heavily occluded in lots of ways, by foliage, by signs. Stop signs can be occluded by cars. Stop signs can be part of cars, and they can be part of cars in an active or inactive state again. Stops can be sort of held by a person. Stops come with lots of exotic modifiers to them. So this stop only applies except right turn. This stop says take your turn through this place. This stop is right turn, keep moving. So do not stop if you're going right. So there's a variety of modifiers, all of them we have to care about because they actually have impact on how you should drive through this point of space. And as I mentioned, everything is AI vision based at the moment. We do have maps, of course, that we build, but they're not high definition maps. But stops can be attached to gates, but they only apply when the gate is closed. When it's open, they do not apply. Stops can be on arms. These arms can lift, and then the stop sign does not apply anymore. Stops can only apply when you're taking a left, so they're action conditional. And so basically there's a massive variety of, even just for a stop sign to get this to work. And what we do day to day in the team is we are going through the long tail and we're building all this infrastructure for sourcing all of these additional examples.
So this clip shows just how tough it is to do one thing well, just to detect stop signs in all the crazy circumstances. Neural networks that do images are fine for that, but look at the number of different ways stop signs can be used in the real world. This is where you can't simulate everything. I mean, just on a basic level, you can't think of all the cases that are out there. And note here that Andrej talks several times about the long tail. This is what many are calling chasing the nines or the edge cases. It's all the nutty edge things that you have to deal with once in a while that aren't common. And don't forget, you need to do this for every country and every language too. Makes me exhausted just thinking about it. The method Karpathy describes for solving this is iterative bootstrapping. You get the general case working well, then you find the edge cases and you train on them. You get those edge cases working, you find more particular edge cases and you train on them, and you keep going and going and going and refining. And they can use shadow mode to help with this, which means that the car is driving under human control, but the computer is making decisions and guessing whether it did correctly or not. So shadow mode, for example, could see where the driver stops, but the car failed to see the stop sign and would have not made a stop. And so it can, flag that as an error. It can then grab that data and it can use it to help itself make the driving system better. And of course, negative cases are useful too. If the car thinks there should be a stop, but the driver or map disagrees with that, that's getting rid of false positives, which is really important. This is where the dreaded phantom braking comes from. You get a false positive identification of a stop sign or something, and it just stops in the middle of the road, which it shouldn't do. So false positives are just as bad as false negatives. And here you can use your drivers. You can create a little mini network that's designed just to detect those stop signs that are a problematic area. You can have this little mini network identify more cases in the real world and upload that back to the mothership. This does not provide perfect data. As Karpathy says, it's noisy data. There's a lot of false positives, but it's enough to extract the needed images to train on. The main networks can then be trained more on these images because you've cultivated those particular images that you need. You can also see that he has a very large collection of stop except for right-hand turns, etc., etc. So it's kind of interesting, all of the weird little modified cases that exist.
We again create a detector for this, and then we get a noisy stream from the fleet of cars encountering except right turn on stops, and then we can label that, incorporate into a training set. We have tens of thousands of these. I'm not actually 100% sure how you build out a data set like this without the fleet. We put just as much work into massaging the test sets as we do into training sets. So just reporting your mean average precision or reporting the loss function that you achieve in a test set, that just doesn't do it for us. So we spend a lot of time inspired by a sort of test-driven development to build out very complicated unit tests and predicates for how the detector should behave in different cases. So for example, we could have a barrage of tests along the lines of, in this image, you should detect a stop sign right here, and the modifier that you, for this and that you predict on the stop sign must be this or that. And so we have mechanisms for creating and massaging these unit tests. It's a growing collection as we encounter problems in the fleet and as we notice them. And then we certify whether this detector is performing well or not. And this is really our test set. It's curated unit tests. If you're in a production setting, we actually break down all these different issues and track them individually and then pursue them one by one with data engine to actually make them work. So occluded signs, we would build out a test set first. We see that we're failing on occluded signs, and then once we have the tests and we're failing them, we then spin the data engine on occluded signs, and then we see that the percent pass goes from 40% to 99% or something like that, and then we're confident that this is actually working relatively well.
This clip I find fascinating. Their team doesn't just take an overall score of the fitness of how their test data does. In other words, how did it do detecting stop signs overall? But instead, what they do is they build out an extremely granular evaluation system. So now we know, how did it do with stop signs in heavy rain? How did it do with heavily occluded stop signs? How about a person holding the stop sign, et cetera, et cetera, et cetera. This granularity can allow them to focus training on exactly where it's needed because they can see where it's failing. That's super cool. If it does bad on rainy stop signs, for example, you can collect more data on that and you can train harder on that area. The training then becomes much more focused, which is much more tractable of a problem. Then Karpathy backs up a little bit to discuss how many of these stop sign type tasks have to be done simultaneously.
So the complexity of this is quite staggering. We have to know a lot about any scene, and each one of those things has their own data engine. So what we end up doing is we have these neural networks that have a shared backbone, and then they're multitask, juggling lots of different tasks. And in total, the team is currently maintaining 48 networks that make 1,000 distinct predictions. These are just the raw number of output tensors. If you just take all of our networks and you add up the output tensors, it's 1,000. And those tensors, of course, can have multiple predictions in them. None of these predictions can ever regress, and all of them must improve over time. And this takes 70,000 GPU hours to train all of the neural nets.
I love this name, by the way, the Hydra net. The Hydra, of course, is the creature from Greek mythology with many, many heads that Hercules fought. So it's kind of the way their system works. It has many, many heads associated with it. You can see from this image there are 48 different networks, and this was before the new beta version, which apparently has a good deal more. There are 1,000 prediction tensors, and it takes about 70,000 GPU hours to train it. And by the way, each prediction tensor can have multiple predictions. And if you recall, a tensor is a multi-dimensional matrix, so it's likely to be very, very large. It's got a lot of numbers in a giant cube or something. Think about it that way. Okay, so this gets us to about halfway through Andrej Karpathy's talk. He's just getting into the meat of it. So if you enjoyed this episode, definitely subscribe for the next one and hit the notification bell so you don't miss it. In the meantime, thank you so much for watching, and don't forget the 10,000 subscriber giveaway. And also be sure to ask me questions in the comments or at my email address, which is DrKnowItAllKnows@gmail.com. Till next time, bye-bye.